Okay, so I want to take a moment to talk about some notation that either I will use or have used and have not yet explained. This notation means A is a subset of the set B. Another way to say this is that A is contained in the set B, or A is included in the set B. This notation, subset equality, B, means that either A is a subset of B or A is equal to B. So from this point forward, this is the general notation that I will use for a subset. Another useful notation is A subset not equal to B, where we put a bar through the equality sign. And this means that A is a subset of B and A is not equal to B. One notation that I've used repeatedly that I have not explained is the notation for the set of integers. So this symbol, an ornate letter Z, denotes the set of integers. The letter Z is for the German word Zahlen, which means numbers. Another useful notation is the existential quantifier with a bar through it, and this means that there does not exist so let's look at a new definition. A subset A of a set B is a proper subset if A is not equal to B. That is, using the notation just described, A is a subset of B but is not equal to B. So next, we'll prove a lemma. If A is a non-empty set, then there exists some element x such that x is in that set A. Now, this is a very good example of something that seems obvious. You may say to yourself, well, obviously, if the set is non-empty, it has to contain an element, but we must be able to prove a statement like this from the fundamental axioms or any undefined terms. Here we'll just need the axioms. So our proof will be a proof by contradiction. So suppose that the set A is non-empty and assume for a contradiction that there does not exist an element x such that x is in the set A. Then, for every element x, that element is not in the set A. And by the axiom of the null set, we have that for every element x, x is not in the empty set. And so the biconditional statement, x is an element of A if and only if x is an element in the empty set, is a true statement because each of the statements is false. And hence, by the axiom of extension, we have that the set A is equal to the empty set. That is, they are the same set. This is a contradiction since A is the empty set contradicts the hypothesis that A is not empty. And therefore, by contradiction, if A is a non-empty set, then there exists some element x such that x is in the set A. Okay, so we'll use this lemma to prove a theorem. So let A be any set, then A is a subset of itself. So our proof will be a proof by cases. So let A be any set, then either A is the empty set or A is not the empty set. So first, suppose that A is the empty set. Then, for every element x, x is not, correction, the implication, x is in the set A, implies that x is in the set A, is vacuously true. So conversely, suppose that A is not the empty set, then there exists at least one element x such that x is in the set A. And so for every element x, the implication x is in the set A implies x is in the set A is true. And therefore, if A is any set, A is a subset of itself. So next, we'll prove another theorem. Let A and B be sets Then the set A is equal to the set B if and only if A is a subset of B and B is a subset of A. So proof, let A be equal to the set B. Then, by the axiom of extension, we have that for every element X, X is in the set A if and only if X is in the set B. So, as X is in the set A implies X is in the set B for every X, we have that A is a subset of B. And because for every X, X is an element of B implies that X is an element of A is true, we have that B is a subset of A. So conversely, suppose that A is a subset of B and B is a subset of A. Then since A is a subset of B, we have that for every element X, the implication X is in the set A implies X is in the set B is true. And as B is a subset of the set A, we have that for every element X, X is in the set B. The implication X is in the set B implies that X is in the set A is true. And so for every element X, we have that X is in the set A if and only if X is in the set B. And so by the axiom of extension, we have that A is the same set as B. A is equal to B. And therefore, we have proved that A is equal to B if and only if A is a subset of B and B is a subset of A. So using this theorem, we can now demonstrate that two sets are equal by demonstrating set inclusion in both directions for those sets. So now let's consider another axiom. And this is known as the axiom of pairing. If X and Y are two sets, then there exists a set containing them. So this axiom tells us that sets are also objects, and so a set can contain as elements other sets. Okay, so we will end here for now. Next time, we will look at basic operations on sets and an introduction to relations and functions. So I hope you have enjoyed the second lecture. Thanks for watching.